This is part of our Simplified revision series. We have done most of the core subjects except for medical imaging, which you are going to do now. Having looking at all the questions from this 4 years of papers, one thing is getting very, very clear. Medical imaging, first of all, they are making the questions very, very, very easy, even compared to bioinstrumentation. Medical imaging questions are specifically very easy. And this is predictable. And there are roughly like 32 questions from 4 years, right? So there are about 8 questions worth anywhere like 13, 14 marks, 8 questions, or around 12 to 13 marks, approximately 13 marks. That makes it highly weighted, very important subject. So it's easy, predictable, and then it's also highly weighted. In fact, it's easier compared to bioinstrumentation, many other scoring subjects. So almost 90-95% of the questions that shows up here can be easily scored. You can get 95% plus in medical imaging questions, theory and numericals. This is easily possible. And what they are specifically asking us, there are lots of questions from ultrasound. There are lots of questions from X-rays. So these two are the most important. And then you have MRI and then radioactivity. These two are the second most important. And then you have CT, image formation and miscellaneous and things like that. CT, image formation and topics like that. And this is what, again, I noticed. What is there in the syllabus is actually a lot, but what they are asking is very, very easy things. Even in ultrasound, MRI. Even if sometimes say the formula are very hard to remember, I will actually say it in a way that is kind of easy to remember. Notice. So again, you have this basic physics, instrumentation, and image formation techniques, right? There are 3 important things here. You need to know the basic physics. Say for ultrasound, sound as a wave and its properties, how it interacts with matter and all that, how it gets attenuated, how it gets reflected, transmitted, and all that. Then instrumentation, a MRI, you're going to use a gradient field, right? How does that affect the slice thickness, things like that. And then image formation. This, quickly, if you know in X-rays, let's say signal is proportional to this, and then noise is proportional to this, you can quickly answer questions like signal to noise ratio, contrast, and things like that, right? So questions are primarily from these 3 aspects, in fact, mostly from basic physics and instrumentation. They are fairly easy to solve. So let's start solving the 3 years of PYQs. Whatever you need, I will kind of highlight it then and there. So this question, 5 megahertz ultrasound pulse is used to image a tumor at a depth of 2 centimeter. Quickly, what are they asking? How long will it take for the echo from the same tumor to arrive at the receiver? They are using a 5 megahertz ultrasound pulse. Instead, a 2.5 megahertz wave is used. Suppose the depth of the tumor and all that remains the same, right? It takes time t for the reflected echo to come back to the receiver. Instead, if this is used, how long will it take for the echo from the same tumor to arrive at the receiver? They are changing the frequency, ultrasound frequency. Will the speed change? The speed will not change. For that reason, the answer is T. So quickly, what does the speed depend on? Of course, you know that ultrasound speed, this depends on the bulk modulus and density, right? And of course, you could also write this as in terms of compressibility, that is 1 over bulk modulus. This is 1 by kappa into rho. Are there any things that depend on frequency? For example, yeah, there are few things that depend on frequency. For example, your loss, ultrasound loss, right? Your alpha, right? Notice this is typically proportional to the frequency. Typically frequency, sometimes frequency power 1 or 2. So you have F power B. And the proportionality constant, we call it as A, right? Notice this loss, you have 2 constants here, B and A. This loss typically is proportional to frequency. This is loss and this in dB per centimeter inverse, decibel loss and centimeter per inverse. That is proportional to frequency. So notice if it is high frequency, it has lesser penetration. because the loss is higher. Low frequency ultrasound, penetration is higher, right? So you have a application where you are imaging skin, you will be using high frequency because you get a better resolution. Deep inside, you will be using a low frequency ultrasound, around 1 megahertz, right? And these two, just for reference, A, AB typically is one. That's typically one. And for now, the speed doesn't depend on this. So the answer here is just the same time. Time doesn't change. Speed doesn't change. Time doesn't change. Next question. So 5 megahertz ultrasound transducer being used to measure velocity of blood. So theta is given, I suppose. Doppler shift is given. Velocity of sound is this. What is the velocity in centimeter per second square? This formula is going to repeat again and again. Del f is 2 cos theta u by c into the frequency of the ultrasound. Let's see, your frequency of the transducer f is given here. This is Doppler shift delta f given over there. Velocity of sound, the c is given over here. Velocity of sound, this is c. And then theta angle is given over here. This theta is given over here. And then what they are asking you for is the velocity of blood flow. They are asking you for is u. That is the velocity of blood flow. So do it in meter per second in SI, and then you can convert that to finally into SI. So notice your u happens to be del f. So I'm just going to do some quick calculations. U was del f into c by 2 cos theta. Yeah, right? This happens to be, let's put everything in hertz. So this is 200 into C. This is in SI, 1500. 2 into cos 60 degrees into the frequency is 5 megahertz. So 5 into 10 power 6. Right now, your answer should be in the same units of C, that is in meter per second. Finally, we can convert that to centimeter per second. So how much is this? I suppose you are getting 0.042 meter per second. That corresponds to, I suppose, 4.2 centimeter per second. So this is a basic relation. You can derive this from, the Doppler shift based on the relative speeds, changes in speeds. You can derive this. I suppose this is 4.2 meter per second. Now, some of this information, specifically this F, can be given based on few other ideas. This F can be given by different means. Yeah, sorry, this cos is 45 degree. The answer still, I suppose, is correct. This F can be given in different ways. For example, in this case, so this is ultrasound, right? Doppler ultrasound. There is also laser Doppler. For example, this 830 nanometer laser Doppler. So again, the same equation, notice your delta F is 2 cos theta u by c into f. But instead of c and f, they have given this 830 nanometers. We know that your c for any wave, c is lambda times f. Speed of that wave into speed of that wave equals wavelength into frequency. So these two, I suppose, can get cancelled, and you can write a lambda here, right? Those two will get cancelled and will have a lambda. And again, you can substitute this to get, I suppose, the Doppler shift. So again, let's do this in SI, hertz, and then we'll get it back, the final answer. This is cos 60 degrees into u was 3 into 10 power minus 2 meter per second. That divided by lambda is 830 into 10 power minus 9 nano. You should get this in hertz. You can write that answer easily in kilohertz. Suppose you are getting, some of you are saying this is thanks. So today we can move faster, 31.6 kilohertz. So you are supposed to be getting 3600 something, approximately 3600. The answer will be 36. So the same equation, but they can give you the F differently. In this case, for the laser Doppler, they gave it using this 800 nanometer. They gave it. So two things need to be noted. One is that it's laser. So we know the speed of laser will be 3 into 10 power. What is the speed of light here? Just in case you need it, what is this speed? See, 3 into 10 power 8, right? And the lambda you are getting from here. Right now, you don't need this information, but just in case, note. But right now, you don't need it, I suppose. Give me 1 second. Now let's look at one more way this is modified. For example, this question: thickness of a piezoelectric crystal will determine the resonant frequency. Yeah, that is essentially how they give that. To work at a resonant frequency of 5 megahertz, the thickness of the transducer should be, right? Yeah, another golden relation here. The thickness essentially is lambda by 2. And we already know that C is lambda f. So you can write this as T by 2f. And the speed is speed of ultrasound in that crystal, PZT crystal. This is, for example, given to be 4,350. Let's be careful about this. This is speed of sound in that crystal, quartz crystal, typically piezoelectric crystal. This is solid around 4,500, specifically 4,350, right? What we need is a thickness. Again, let's do that in meters and we can enter the answer. So this happens to be 4,350 by 2 into the 5 megahertz. So 5 into 10 power 6 meters. How much does this correspond to? This number as such, I suppose, is 0.435 into 10 power minus 3 meters. So your answer should be 0.435 mm. Fairly easy, right? So given D, you can find F. In this case, given F, we found D. You can also, given D, you can find F. They can club this question and, the very first question that we saw. They can club this question and this question. Is there an example like that? Yeah, PZT crystal of thickness 1 mm and wave velocity 4000 is emitting a longitudinal pressure wave, which is incident on blood vessel at 30 degrees. Doppler shift in the ultrasound wave. What we need is a Doppler shift. Blood flow velocity is given, and then wave velocity in soft tissue is given. 2 cos theta u by c. This is the wave velocity in soft tissue into the frequency. We just saw that you could write d as lambda by 2. Then you have c as, this is CPZT, that is lambda times f, right? So this f, you can write it differently. Notice this will be 2 cos theta u by c soft tissue into this f should be, let's write this here. This is CPZT by lambda. And suppose 1 by lambda, you can write it as 1 by 2d, right? So you can also make that conversion. So this, we can write it as 2d. Just replaced lambda over there to show that. Let's also. So lambda is 2d. I made that substitution. Now we can plug in all the numbers and get what this is. So what is 2 into cos 30 degrees? Your get calculator can distinguish degrees and radians, so be careful about it. Cos 30 into u is, I am running short of space. Real estate issue. Notice this equals 2 into cos of 30 degree into, this is 10 into 10 power minus 2. So that is 0.1 meter per second. Into PZT is going to be 4000 in meter per second, everything in SI. So I'm going to get answer in SI. This by of tissue 1540 and 2 into D happens to be 0.001. You should get the answer in hertz. And I suppose this is 225. 225. You'll get the answer directly in hertz. So they can mix and match pieces, this equation, right? And this equation. 225. Yeah, you're within the key range, I suppose. 224.94 is this. 25 should be within the range. Let's go to the next question. Ultrasound transducer with a 3-cycle long pulse into a soft tissue at normal incidence at fat liver. So this is normal incidence. This is fairly easy. Axial resolution and the amplitude reflection coefficient. So for one pulse axial resolution, this is lambda by 2. If there is like one cycle, but this is 3-cycle long pulse, right? So we'll multiply by whatever the number of cycles is. There are 3 pulses, so we'll multiply by that number of cycles, 3 here. This is fairly easy to find, I suppose. Yeah, let's quickly find it out. This happens to be 3 into lambda. You could write it as c by 2f. Speed, I'm going to use the speed tissue. Even if we use any of these other numbers, you'll be getting 0.5 or 0.75 differentiation you should be able to make. So I'm going to use this c by f. Again, if you're wondering, okay, c by 2f. My C is 1500. Everything in SI, my F is into 3 into megahertz, right? 3 megahertz. I should get this in meters. Suppose in I suppose this is 0.75 into 10 power minus 3 meters. So your actual resolution, hey, can someone quickly do this? Yeah, this is 1500 by 2, 75. Yeah, there is a question doubt in the previous one. I'll quickly answer that. So this is 3 cancels 1500 by 2. This is 0.75. So I know the answer is this or this. Now we have to find amplitude reflection coefficient. So amplitude reflection coefficient, they can ask you many things. Notice typically there is a question from this amplitude reflection coefficient this year. Then there is sum of amplitudes and of reflected and incident wave this year. And this year they asked you the intensity transmission coefficient, right? So there are this bunch of formula. I'll kind of tell you a very simple way to remember that. So far we have found this, whether it's 0.22 or 0.11, we have to make a calculation. Right now, let's do the amplitude reflection coefficient. I'm going to write this as R. Let's also have quick reference over here. This is what happens is you have some medium, have an incident wave. Part of it gets reflected back, part of it gets transmitted. So you have an incident wave, you have a reflected wave, you have a transmitted wave. The amplitude reflection coefficient, R, is a ratio of amplitude of pressure that is reflected with respect to amplitude of pressure that is incident. This happens to be Z2 minus Z1 by, so you are always going to need to calculate this Z2 minus Z1 by Z2 plus Z1. You're expected to calculate this and your Z is not given. That is fine. Z can be found from rho and C. Specifically, your Z is rho times C. So you have the medium 1 where things are incident, then medium 2 where things are transmitted. You can quickly calculate this. I need, some of you are saying the answer is T 0.11, but can we show some intermediate values? Specifically, can we show how much is Z2? Actually, the units and all that doesn't matter. You put it in SI. This is a non-dimensional thing. It's a ratio. It will get cancelled. So rho C and all that you can easily multiply. But let's just show what is Z1, what is Z2. Notice this is fat liver interface. So fat is 1, then liver is 2. So your fat is 1, your liver is 2. So Z1 is 1450 into 920. That happens to be in arbitrary units, 334. There are 3 zeros following, but I don't have to exactly write it because it will get cancelled, right? Z2, the 3 zeros, I don't have to write it because I'm looking at a ratio. Z2 is 1570 into 1060, 1664.2. 1664.2. Of course, 164,200. I'm writing it in consistent way. So now you can calculate Z2 minus Z1 by Z2 plus Z1. That happens to be, so 1664.2 minus 1334 divided by 1664.2 plus 134. That happens to be 0.11. Just count this to be 0.11. So the answer here is, but as I pointed out, they can ask you many other things here. But this is the starting point. If you remember this, getting other relations is going to be very easy. I'll show you how to kind of recall the other relations based on this. That is point number one. I'll show that to you. But right now, the question is, if this is not mentioned typically, what is really safe is this. They aren't mentioning it. They should likely give you a little bit of range on either side. So 224 point, to be on the safe side, you can do one decimal. People prescribe two decimals, but if they are not specifying anything, as far as they specify the units, you can give it to up to one decimal. And in this case, let me also say what the answer range is. 8 p.m. 2021. Yeah, they are giving a reasonable leeway on either side. Notice the answer key range is from 222 to 228. So 224.9, 225, all of that will safely fall within the range. Shouldn't be any issues. Now, getting back to this, how do we recall the other things and what are the other things there? Let's quickly do that. So you start with this. Your Z is rho C. Then this is a starting relation as Z2 minus Z1 by Z2 plus C1. This is ratio of amplitudes, R by Pi. Then you have P transmitted by P incident with respect to P incident. This is T. This is just happens to be 1 plus R. So if you know R, you can calculate this. So this is ratio of amplitudes. Based on this, you can calculate a ratio of intensities. Right. So your reflected intensity by incident intensity is just square of R. And energy conservation will say this I transmitted by II, intensity transmission coefficient. This is a reflection transmission, intensity reflection coefficient. This is amplitude reflectivity, amplitude transmittivity. 4 things. This typically we refer to this as I. And then we refer to this as Ti, intensity transmittivity. You can, again, this intensity and that intensity is conserved. So this happens to be 1 minus Ri. So starting with R, if you know this, you can get Ri, squaring it. You can get T by just adding 1 to it. You can get T. You can also get Ti. Let's say this is Ti. You can get Ti by doing 1 minus Ri. The expressions, if you actually substitute for all the expressions can get messy, but this is an easy way to remember. I am also given it along with the definitions. So this is expression, the main expression. Using that, you can easily find out what this is. You can find out what this is, right? And you can also find out what this is. And all of this is for normal incidence. Wave is hitting at 90 degrees, partly gets reflected, partly gets transmitted. For non-normal incidence, all of this holds good. This relation holds good. This relation holds good. This relation holds good. You need to slightly modify R. For non-normal incidence, I suppose there is a question. We'll answer that. In this case, for example, they have mentioned non-normal incidence. Notice what they are asking for is, one is we have to find the degrees. We have to use Snell's law for that. I'll show that in a moment. But they are asking you for intensity transmission coefficient. They are asking you for Ti. They're asking you for Ti. Ti. The way I would get that is, of course, notice Ti, I just said this is 1 minus Ri. Ri is just square of R. So if we can write, you can easily get Ti, right? Ri is just square of R, right? The R for normal incidence happens to be this. Let me actually write the whole thing. R for normal incidence happen to be Z2 minus Z1 by T2 plus C1. For non-normal incidence, you have a cos, and you have, let's put theta also, cos theta, and this is IT, income tax, information technology, whatever, right? IT. 2121, and then this is IT. What is this? Let's say this is a surface normal. Something is, incident at an angle theta. This is theta incidence. Theta reflected, that's going to be the same thing, right? We know this is theta reflected. Part of that gets transmitted. This angle, right? This is theta t. So we have theta I and then theta t. Theta transmitted. So notice the Z muscle, kidney. So this is interface between muscle. This is traveling inside muscle. So muscle is one, and then kidney is 2. And then one more thing, this theta I is not given, right? Or theta I is given, I suppose. Incident at 60 degrees. Theta I is 60 degrees. This is theta I is 60 degrees. You don't know theta t. How do you find that? You use Snell's law. So go from here to here, and then using this, find this. This is what they want at the end of the day. And you also need theta t. That is fairly simple. You have blank space here. Yeah. Sin theta I by sin theta t equals C1 by C2. But theta 1 by theta 2 equals C. Now these two angles are same. Theta R equals theta I, right? Incident equals reflected. Only the transmitted changes. The ratio of those two will be depend on the speeds. This comes from Snell's law. Most of you are aware of that. And because I'm writing this for the first time, I'm also going to box this. So the two speeds are given, right? The two speeds are given, C1 by C2. You have muscle speed C1, kidney speed C2, and then theta I is given, you can find theta t. Can we quickly find what is theta t? It cannot be, it's not 60 degree. I don't think it's 30 degree also. C2, this is 1560 divided by C1, that is 1590 into sine of theta I, the sine of 60. 0.849. That is sine theta t. If I take sine inverse, I get 58 degrees. The answer is between these two. Now I have to find, I know both theta I and theta t. At this step, I have to find R, RA, and then TA. And can anyone tell me what the answer is here? I can also do the calculation while I wait. If I get an answer, I'm going to just take it off. Or this is 21. Suppose 0.94. Thanks. This is TA happens to be 0.94. So the answer here will be C. Hey, notice the expression for TA for non-normal incidence is very complicated, but I did it. And if you find R, you can easily find RA. If you know RA, you can easily find TA, right? You can square this and do this. So this non-normal, this relation also Z2 minus Z1 by Z2 plus Z1. Just that there are cos theta. You have theta I minus theta t, theta I plus theta t, right? So with that, you can answer any of the four things. And typically every year they ask you one. You can technically answer any of the four ratios. But they always ask ratios. No, there is a big example, right? Ultrasound plane wave of amplitude P0 hits a semi-infinite boundary of two media having acoustic impedances Z1 and Z2. Some of the amplitudes of the reflected and incident waves. What you need is PR plus PI, right? So quickly, PR by PI. This is known as R. This is Z2 minus Z1 by C2 plus Z1, right? So your PR is just PI into this number. Now, if you add PI to both the sides, you get the required thing. You added PI to LHS. If you add PI to RHS, you get this. You can take PI common. So this is 1 plus R. That I suppose is incident is given to be P0, right? So let's also be incident in the question terminology is P0. Incident is P0. So I suppose this is Z1 minus Z1 will get cancelled to Z2. Suppose the answer is A. Let's do it over here. Answer is PR plus P0. If I take P0 common, I have 1 plus Z2 minus Z1 by Z2 plus Z1. That is just 2C2 by Z1 to C2. So they can also ask you, cook up a thing and ask you for this. That's all from ultrasound. Any variety you can easily score. Let's go to X-rays. X-rays, what do you need to? X-rays actually you have much lesser things to remember. Diagnostic X-ray imaging, the following is not a part. Primary EM interaction in soft tissue. Photoelectric is a part, so this is not an answer. Compton scattering is a part, this is not an answer. In production, characteristic radiation production, this happens in X-ray production. To some extent, this happens in X-ray production. What they are asking for is EM radiation interaction with soft tissue. Compton, Rayleigh, photoelectric is there. This is there in production, X-ray production. So for that reason, typically it's not a part. Pair production, notice this is 2 into 5 lagman kilo electron volt energy is generated in pair production. This is pretty high. This is about 1 mega electron volts. And this is quite high for diagnostic X-rays. So again, this doesn't show up. For that reason, this is too high in energy, too high energy for diagnostic purposes production. Where am I getting that from? I'm getting this from 2 times this is pair production annihilation. This is 2 times mc square for electron, rest mass energy for electron, right? That will happen to be for 1 electron, it will be 1 kilo electron volts. Electron positron or electron positron pair together will be like 2 into 511 kilo electron volts. So too high energy for diagnostic purposes. So again, this cannot be an answer. This was an MCQ, but the key said even, this happens in production, not in tissue interaction. So technically, this is also fine. They also put this in the answer key. I think they only asked an MCQ, but either this or that was there in the answer key. Technically, they should have made it MTA, but this is the answer key. And also that's explanation. So let's move on. Using fast X-ray screen improves resolution. So quick analogy, fast X-ray screen. Fast X-ray screen is like high ISO. If you know this thing called, you're taking photos and all that, in your camera, you have this thing called ISO, sensitivity of the sensor you're using, right? Sensitivity is very high, resolution is bad. So fast X-ray screen worsens resolution. Which of the things are correct, right? It worsens the resolution. Decreasing the tube current decreases signal to noise ratio. So your signal intensity, right? This is proportional to current, tube current, into the time for which you apply that current. So notice product will be a charge, right? Into the voltage applied in the tube, X-ray tube. So higher the current, higher the intensity. Higher the intensity, higher the signal. So decreasing tube current decreases signal. So that is a quick, and this is what typically happens at the source. Intensity of the source, that is at the tube. Next question, half valley layer. In nuclear imaging, sodium iodide crystals are used to detect gamma rays of 180 kilo electron volt. Percentage of gamma rays that will pass through 1 centimeter of sodium iodide crystal, assuming half valley layer is 0.2 centimeters. Is fine. Your n as a function of distance happens to be number of photons that remain as a function of distance is initial photons, kind of decays exponentially, minus mu times x, mu times the distance it travels, right? And mu is this linear attenuation coefficient. It is related to the half valley layer. Specifically, at x equals 1 hp at a distance of 1 half valley layer, your n of x is essentially half. The definition of that. You can use this, and this will quickly imply a relation between mu and half valley layer. You can either do it this way, or you can also, this is 0.2 centimeters is the half valley layer. There are 5 half valley layers. 100 becomes 50, 50 becomes 25, 25 becomes 12.5, that becomes 6.25, right? At the fifth step. You can either do it that way, or you could also, this will imply your HPL or mu, doesn't matter, mu happens to be ln 2 by HPL. So HPL is 0.2, your mu happens to be, if you calculate mu, this will happen to be ln 2 divided by 0.2. I get 3.4657. 3.4657. What we need is n by n naught into 100. And n you are calculating at 5 HPL. Substitute x is 5 HPL, you know mu, when you don't have to technically calculate this and substitute it, right? You can write mu as ln 2 by HPL and some of them will get easily cancelled, right? So this is what you want into 100%. This will happen to be power minus ln 2 into 5. E power minus 2 power 5, 1 by 2 power 5. Again, boils down to the same thing, right? 1 by 2 that raised to the power of 5 is 0.03125 as a percentage. This is 6.25 becomes divided by half. This is 3.125. You could do it this way, or notice, do we have space? Yeah, I have space here, right? 100 at first half value layer becomes 50, at second half value layer becomes 25, third half value layer becomes 12.5, fourth half value layer becomes 6.25, fifth half layer becomes 3.125. So this is your answer. You start with 100%. You could also write it down that way, but what I did is a slightly better way of doing. And quickly notice, so there is a relation between half value layer and mu. That is also quite evident here. Inverse square law has a practical use in radiography while taking an acceptable chest photograph of a subject at a distance 0.75 meter. X-ray source settings were kept at, notice this is a voltage and this is current into time, milliamp second, right? 50 milliamp second. 50 kilovolt peak at 50 milliamp second. Subject is moved to a distance of 1 meter and your voltage is kept the same. The new value of MAS, right? So in simple English, inverse square law, what this says is this intensity at a distance d is take the source intensity, that divided by 4 pi t square. And this S is at the source. Consider a sphere, take the source intensity divided by the area of the sphere, you get intensity at some other point, right? So you want the same exposure at a farther distance, right? To get same exposure at farther distance, you need higher current. How much higher? It drops based on the square of t, right? So you need a 1 by 0.75 square improvement, 0.75, 1. Right? You need this much improvement from the initial current. The other 50 is not changing, right? From 50 millisecond. And this 2 is coming from the inverse square law. You can technically write it a I d1, I distance 1, then I source 1 by 4 pi t1 square, I d2 is this, and then I s2 by 4 pi t2 square. Then you can divide these two and also realize I source, I just said this is proportional to current into time, milliamp second, into voltage peak, kilovolt peak typically, right? You can substitute it right there, but in simple English, to get the same exposure at farther distance, intensity is dropping a square. So you need 1 by 0.75 ratio of the distances squared into the initial current. Other thing doesn't change, right? This happens to be 1.33 square, 1.7778. That into 50 gives you 88.89. Gives you 88.89 milliamp second. Radiographic system is operating at this. So notice you can use aluminum. Safety is defined with respect to aluminum. So to have the same effect as aluminum, if you are using some other metal, copper, how much thickness it should be, right? That is, notice, n happens to be n naught e power minus mu x, right? This initial thing and all that is same. Thickness of the new, right? It needs to have the same filtered energy. That is, what comes out is the same. Keeping the initial same, you are not also changing the initial. Change the initial again. You have to, this initial doesn't change. That means these two has to be the same. This power has to be the same. What it says is mu into aluminum x aluminum. Linear attenuation coefficient of aluminum to x aluminum has to be same as linear attenuation coefficient of copper into thickness of copper. There is one small catch here. What is given as mass attenuation coefficient, linear attenuation coefficient happens to be, take the mass attenuation coefficient, multiply that by the density. Mass attenuation coefficient, notice, is in this is essentially mu comma rho. That's a subscript that is just mu normalized with respect to density. If you multiply these two, you get mu. Mass attenuation. This is mass attenuation coefficient. This is mass attenuation coefficient. And this is linear attenuation coefficient. Linear, or this is linear attenuation coefficient. You can find the two linear attenuation coefficients, divided by the thickness, that is 2.5 mm. You will get the answer and for copper. In fact, let's give some intermediate numbers. Mu Al, mu Cu. So product of this is a function of this X-ray energy, right? Or the operating voltage. Specified as operating voltage in this case. This is for the aluminum. This is 0.02015 into its density, that is 2699. P4.38 meter inverse. For copper, this is 0.07519 into 8960 density. This is pretty high. The copper is pretty high. But see, copper, you might need a lesser thickness, but you have to be careful with copper because there can be, I suppose, characteristic radiation. So if you're using copper, you might want a small layer of aluminum on top of it. This is 673. By calculation, your answer that you want is 54.38 into thickness of aluminum, that is 2.5, divided by attenuation coefficient of copper, that is 673.7. You should get the answer in mm. That happens to be 0.2. That is point number 1. 0.2. I just found out this from this equation. Other things are known. This known. XAL happens to be 2.5. So this is from the theory side. That is from a numerical side. But from a practical side, copper alone is not recommended, because I think this characteristic radiation for copper happens at the moderate low energies, about 10 kiloelectron volts. That is not good for the body. So even if you're using 0.2 mm thick copper, you need a very small layer of aluminum to filter that additional, any characteristic radiation. To filter that, you need additional AL. This is from a practical side. From a theory side, I think we have answered it. Let's go to this question. So now they are mixing geometry and the same idea. Geometry plus attenuation. That is this question. So many students found this question somewhat puzzling. Yeah, they are specifying distance using crazy geometry plus the well-known attenuation, right? Sort of a quantitative aptitude problem combined with this X-ray, right? Which is where students get confused. It's a combination. I am not able to understand, what they are describing. I'm not able to convert the text into equations, right? What they are saying is circular disk, uniform absorption coefficient. Consider a single ray passing through the disk in the plane of the disk. The shortest distance from center of disk to the ray is t. So the perpendicular distance between the ray and that is t. So this is t. The perpendicular distance. The shortest distance is the perpendicular distance. And then the radius of the disk is r. This disk is r. That automatically says the distance the ray travels is 2 times this side. Notice this happens to be twice one of those things. That happens to be r square minus t square. I'm just using Pythagoras relation, right? So ray kinda enters this way, exists this way, the total distance it travels is twice, the base of one triangle, smaller triangle. The distance, what you have to find is, rest is easy. I naught incident, what comes out, what transmitted is what is incident, a fraction of that. E power, this is in terms of intensities, even if it's log base doesn't matter. Technically, this is e power mu d. So you have I naught, I naught exiting, I incident, I naught exiting, e power mu d. Then you can complete this I naught by I as e power minus mu d. Technically, ln of I naught by I happens to be minus mu times d. So I by I naught, if you put a minus here, that's proportional to d. There are a couple of constants missing. I suppose it's proportional to is what they are asking. This needs to be in base e, and then there is also a proportionality constant. So I suppose this is at best proportional to. The option would be notice this is proportional to d. Even if this is absorption coefficient, this is still e power. There will be a factor there. There will be a absorption coefficient. Mu happens to be 1. Mu happens to be 1. So yeah, suppose this base is in E. Yeah, mu is given to be 1. Make sure that this mu happens to be 1. Yeah, then we'll presume this is in base E. Absorption still is prescribed in terms of e power. It's more. X-ray radiography scenario shown in this. Number of incident photons is what shows up here is 2 into 10 power 6. So we are only interested in this answer as in 10 power 6. For that reason, let me not worry about this 10 power 6 right now. So what is here in units of answer? 2 shows up. 2 photons. 2 into 10 power 6. What exits here is what shows up and then what gets attenuated. This is e power minus mu x. That happens to be is mu is also given. Can we write the mu here? For tissue, this is 0.4. For blood, I suppose this is 0.2. For blood, this is 0.2. So you have e power minus 0.4 into 0.2. That is what exits at the soft tissue at this interface. That is also what enters the blood at that interface. So what exits here will be take this into e power minus thickness of that blood 0.5 into attenuation coefficient, that is 0.2. This is what enters the soft tissue here, but what we need is what exits the soft tissue, right? Is what enters the soft tissue. What we need is what exits the soft tissue here. And that would be, so take this, it will be a fraction of this into e power thickness of soft tissue 1 into its attenuation coefficient, that I suppose is 0.4. So the powers and all that gets added up. Notice, so for non-homogeneous medium, and the medium is not the same, what happens is typically n is n naught e power minus summation of mu I xi. If mu I is not a constant, it's varies from location to location, you do an integral. That is, this is n naught e power minus integral mu of x dx. In this case, notice you just get a summation of this. The answer can be calculated as 2 into e power minus of 0.4 into 0.2, 0.08 plus 0.5 into 0.2, 0.1 plus 0, minus 1 into 0.4, that is 0.4. So I have 0.08 plus 0.1 plus 0.4. 0.58, e raised to that minus of 0.58. That is 0.5598 into 2. What do you get? 10 power 6 is common to both the sides. I am getting, anyone? 1.11979. 1.1 up to 2 decimals is 1.1. That is what shows up towards the end. So to be color consistent, let's write it 1.12. Non-homogeneous media is fairly simple. That is, medium is changing. Non-homogeneous, genus, that's fine. The powers, the product of the exponentials, the power is get added up. That is what I have written here. If it is continuously varying, the summation becomes an integral. This is a bit confusing. I replace that summation with an integral. And here mu is varying continuously. Notice this thing again repeated, right? Normally incident X-rays of energy 150 passes through a tissue phantom detected by a detector. The phantom consists of two material, I suppose. Material P, tissue P, this is absorption coefficient 1. So this is 1 centimeter inverse, 1 centimeter inverse at absorption coefficient, attenuation coefficient, doesn't matter. And then thickness of 1 centimeter, and then absorption coefficient of Q is 10 centimeter inverse, 10 centimeter inverse. What you want is what shows up at the detector. Fairly simple. What shows up here, and then we'll calculate what shows up here. What shows up here, 140 enters. The fraction that shows up at this boundary is just e power 1 into 1. That enters region Q. So what shows up at this boundary is e power minus 2 into 10. Can we calculate this? Again, it's 140 into e power, summations. Notice this is going to be 140 into e power minus of 1 into 1 plus 2 into 10. So shift e power minus 21 into 140. I get 1.06 into 10 power minus 7. 10.6.62. 10 points rounded off to 1 where I get 10.6 to 10 power minus 6 electron volt. Can someone again confirm that? No, 6. How come? Centimeter 10, 1, 1, e power minus 21, right? Yeah, I am getting 7.58 into 10 power minus 10. If I multiply by 140 into kilo, something was odd. This is 140 into kilo. So this is 140 into 10 power 3. And the number that I am getting here is 1.06 into 10 power minus 4 electron volt. That happens to be 106. 106 rounded off to this in micro electron volt would be 106.1 into 10 power minus 6 electron volts. That is micro electron volts. Yeah, my bad actually. I kind of overlooked the scale. This is X-ray detector. The last question, wavelength of an electron volt. Notice you cannot use C equals lambda F, right? The C is not equal to 10 power 8 meter per second. This is not light. So you cannot use C as this and then try to find that by any of that. This is not light, photon. You have to deal with that appropriately. This is quickly, it's accelerated to a potential. The energy gained is Q times V. This is the energy supplied to the electron, Q times V. It's, this charge is accelerating in a potential volt of V. That should be equal to the kinetic energy gained by the electron, that is half m velocity square. And for a particle, you have this de Broglie wavelength. Lambda is h by p, where p is the momentum, right? To get the momentum here, notice quickly 2q volt equals mv velocity square. If you multiply both sides by m, you get p square, right? So given the, easily write your lambda to be h by square root of 2qvm. The h is given, Planck's constant h is given, q is given, this is your q is given, and then mass of an electron, this is also given, m is given, this is 1 volt, v equals 1. So this h, all of this, right? You can calculate lambda. Need that in nanometers. Do that in meters. finally write out down in nanometers. Let me quickly find out. So 2 into 15 into 1 into mass, 9.11 into 10 power minus 31. If I take square root of that, I get some number divided by that. It goes to the denominator, that multiplied by Planck's constant. That is 6.63 into 10 power minus 34. You get 1.2279, 10 power minus 9. Up to how many? Two decimals, 1.23 nanometers. What I'm getting here is 1.23 nanometer into 10 power minus 9 into 10 power minus 9 meters. So the answer should be 1.23. I think key range is 1.2 to 1.25. So we are, I think, fine. What's the time now? 8, right? Let's do one thing. So we are done with two major things, right? We are done with ultrasound and X-rays. What is left is CT, radioactivity, and PET. Let's do CT and then information. CT, I think the questions have been fairly easy. Two-dimensional square plate contains a circular. Actually, CT and all that, they are asking very basic questions. This is 20 by 20, and there is inner circular inclusion with a pi mm dia. There is inclusion of pi mm dia, and then your X-ray beam is of sufficient width, that is 30 mm. It will cover this field of view. What is the minimum number of views? This is to locate a tree in a park, you need at least 2 side views, right? The answer here is 2. So we did this. Your friend went to a park and took photos of the park, right? Trees in the park. From the photos, can you infer the location of the tree? You have a west side view and a north side view, right? If you have at least 2 views, you can locate a single tree. There are more trees. Sometimes to avoid ambiguities, you need more views, right? For one tree, 2 views, suppose. You can get both the X location and the Y location. You can get both the X location and the Y location. So 2 views, no issues there. First generation CT scanner used to point X-ray source as a detector. The source detector assembly can move linearly at a speed of 0.5 meter per second. It takes 0.5 seconds for source detector assembly to rotate one angle. It has to move linearly. It has to rotate angularly, regardless of the angle. Time takens are given or speeds are given. Scanner is expected to 360 projections over 180 degrees span. To cover 180 degrees, it has to do 360 projections. Field of view is for data collection has a diameter of 0.5. So this field of view says how much it has to move, translate. What they are asking for is the scan time. Scan time, this will be equal to 2 things. One is translation time plus this rotation time, angular rotation time. Rotation, it has to do 360 projections. So it has to rotate 360 times. So this is 360 into 0.5. It's fairly easy to calculate. 360 into 0.5. One rotation takes 0.5 seconds, 360 rotations, 360 into 0.5, 180 seconds. And this translation time, notice one translation from the field of view information, it has to move 0.5 with a speed of 0.5, right? So one translation takes 0.5 by 0.5. I'm using speed or distance by speed, right? It takes 1 second. Each projection has to do a translation. So there are 360 translations. This corresponds to 360 into 1 seconds. So the total would be sum of this and this, I suppose 360 plus 180, that is 540 seconds. These two happens to be 540 seconds. And your question is fairly simple because this is first generation. Typically, if it is second generation, instead of taking 1 point at a time, it can do like 5 points at a time or 7 points at a time or 9 points at a time. In that case, the scan time gets divided by that. Let's say there are like array of 9 detectors. Scan time will get divided by 9. Say if you're doing this calculation for a second generation, it is doing 9 points at a time. That means, this 540 here, it's doing 1 point at a time, right? So for a second generation scanner with array of 9 detectors, that will take, let's say, 60 seconds. Here in this case, it takes 540 seconds. Are there any questions?
Sir, can you please go to that circular disc question from X-ray? I got a little bit confused.
Yeah. So I didn't do one step. Let me also complete it. So that means ln IA by I naught equals D. Let me also write this is log of to the base E is D. Yeah, what is your confusion?
Sir, is it? No, sir, no, sir. I got clear. Thank you, sir.
I didn't add one step. I didn't like do it. I took the minus to the side and answered, right? Was that your confusion or was it something else?
Yes, sir. I got confused in the same.
Your confusion. Fine. So I think even absorption, this is not in powers of 10. As far as I know, this is still in powers of E only. So perhaps the log base is not mentioned. It has to be log, but other than that, obviously, you can. These are not the correct answers. Yeah, but fair point. They asked log IA by I naught. I had done till I naught by IA. I took that minus and kind of answered. Fair question. So if there aren't any other questions, we are also done with CT, right? What is left is radioactivity in MRI. What we'll do, let's stop here. We'll come back and do this in part 2. That way the file sizes and many of these things are kind of manageable. So as I said, all the formula that you need for medical imaging is available in that one file. I'll share it. 95% of questions are showing up from that. And it's very, 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 very easily scoreable. And you even notice so far the questions has been very, very easy. So it's a very easy subject, predictable questions. You can easily get like about 13 marks, right? With math or aptitude, you can actually clear the exam. Bioinstrumentation and all that, if you know your, bioinstrumentation, circuits, biomechanics, biomaterials, HAP, right? If you can answer some of those questions, actually, you can get single digit ranks, right? This is very easy and predictable. Also, many questions. So make use of that. We'll come back and do part 2 next week.